So far we discussed about decimator, interpolator, and next we'll discuss about sampling rate conversion by factor I by D. So when we want to achieve sampling rate conversion by factor I by D, by rational factor I by D, we have to cascade both decimator and interpolator. So in the interpolator, upsampler is the first block followed by the filter. In the decimator, first block is filter and second block is the downsampler. See here, interpolator rate is given by I into Fx, whereas here is the decimator rate equals to Fx by D. Since it is already interpolated, you are getting I Fx by D. Otherwise, it is Fx by D. See, the frequency response H of omega V of a combined filter should ideally possess the frequency response characteristics H of omega V equals to I when omega V is from 0 to minimum value of pi by D and pi by I. Since for the interpolator, low pass filter is at the second stage, and for the decimator, low pass filter is at the first stage. We are cascading it so that we get a sampling rate by factor I by D. Same thing, same discussion will go here also. So in time domain, the output of upsampler V of L equals to X of L by L for L equal to 0 plus or minus F plus F 0 otherwise. And the next one is filter. So omega of L equals to, so here it is W of L equals to sigma K equals minus infinity H of L minus K to V of K. So this is output of filter. And finally, the output of sampling rate converter, it is sequence Y of M, which is obtained by downsampling the sequence W of L by factor D. So finally, we get Y of M equals W of MB. So from this, you see W of MB. Substituting here, we are getting Y of M equals to sigma K equals minus infinity H of MB minus Ki dx of K. And expressing this one, MB by I minus N equals to K. So what is this notation is that it denotes the largest integer contained in R. So rearranging this equation 4, we are getting Y of M equals to sigma N equals to minus infinity H of MD minus K. What is K? MD by I minus N. Into I means MD by I into I plus Ni into X of K is MD by I minus N. So this notation indicates largest integer contained in R. So finally, so MD minus MD by I into I equals to MD, that is modulo I. So finally, you see equation 6 can be expressed the Y of M equals to sigma N equals minus infinity H of Ni plus modulo I into X of MD by I minus Yeah. Since it is sampling rate conversion by factor, Bayesian factor I by D, we have to combine the results of both interpolation and decimation process. So finally, we see y of omega y equals to I by D to x of omega y by D, where omega y is from 0 to pi and pi d by I. So any doubts, man, regarding these three topics?
No, sir.
So last one is filter design and implementation for sampling rate conversion. So first one is direct form FIR filter structures. The system function of this direct form FIR filter structure is generally h of z equals sigma k to the power minus 1, h of k to the power minus 2, where h of k is nothing but the unit impulse response of FIR filter. The low pass filter can be designed to have linear phase. What it means? A specified pass band ripple and stop band attenuation. So you know that low pass filter, pass band followed by stop band. So the inefficiency results from the fact that from FIR design is that upsampling process introduces I minus 1 zeros between successive points of the input signal. As already discussed this point. See, this is the figure showing right form realization of FIR filter in sampling rate conversion by factor I by D. So in the previous topic, what we discussed is sampling rate conversion by factor I by D, wherein we are cascading interpolation and decimation concepts. So first one is upsampler followed by filter, again filter followed by downsampler.